Hi everybody. We are now continuing on with our fifth lecture in this series of from kinematics or motion. And this one, since we have already learned what acceleration is, we're going to now learn to interact with that acceleration vector using velocity vectors, displacement vectors, and all this other kind of stuff, using velocity versus time graphs. And motion diagrams, as well as equations. So we're going to wrap all those together, okay? Last time we saw that we did this problem where we had an initial velocity vector, and that acceleration, which is a push or a pull, is adding a positive 2 meters per second velocity to the initial velocity vector for every second. So in other words, you're moving with an initial velocity of positive 1 meter per second, and then after that first second, acceleration is going to add a 2 meters per second velocity to that initial velocity vector to make 3 meters per second. And then starting with that 3 meters per second, that acceleration vector is going to add again to that and create a new velocity vector of positive 5 meters per second. Positive 5 meters per second is your new velocity vector. You're going to add another positive 2 meters per second for every second to that to become positive 7 meters per second. Okay? Another way to calculate if you have a starting velocity of positive 1 meters per second and you're going to be accelerating for 3 seconds, what you could do is take 3 of those acceleration vectors, add it to your initial velocity vector, and that will be your final velocity at the 3-second mark. Okay? So you don't have to do all this to get right to the 7-second, the final velocity. If you know the initial velocity, if you know the acceleration, you could take the number of seconds, and that will be the number of acceleration vectors that is adding to your initial velocity, and that will tell you what your final velocity is. If you want to know what your velocity is after 2 seconds, well, you just take the initial velocity vector and add 2 of those acceleration vectors to it, and now you have 5 as your velocity at the 2-second mark. Okay? In a velocity versus time graph, what this will look like is you start out with a positive 1 meters per second at 0 seconds, and at 3 seconds, you're moving at positive 7 meters per second. The slope of this line is your acceleration vector. Okay? And the slope of this line is going to be positive 2 meters per second for every second. Okay? This is a line, and we're going to do a linear fit, so this is going to be y equals mx plus b, except b now is the y-intercept is your initial velocity. The slope is the acceleration, the y-intercept is time, and that final velocity is what you're trying to predict. So in this case, our initial velocity, or y-intercept, is positive 1. The slope of this line is positive 2 meters per second, positive 2 meters per second velocity for every second, and then time is here. So again, if we pop in 3 seconds here, 3 times 2 is 6, plus 1 is 7, and now we have our final velocity. Okay? What slowing down does, and we saw this last time, is it's subtracting a velocity vector at every instant in time. So if you start out moving to the right at positive 7 meters per second, and you're being pushed to the left by negative 2 meters per second for every second, well, positive 7 minus 2 is equal to 5. You started here, you walk to the right 7, you walk to the left 2, Now you started here and you ultimately ended here, and that's positive 5 meters per second. So now you're moving at positive 5 meters per second at the 1 second mark. Now you're going to add that negative 2 meters per second to it, and that is your new velocity at the 2 second mark. At 2 seconds, you're now traveling at 3 meters per second to the right. You get pushed to the left by negative 2 meters per second over a period of 1 second. And now your final velocity is positive 1 meters per second. Okay, so similar to last time, if we take our initial velocity vector and we add we subtract 3 acceleration vectors for it, 1 for every second, then we have a final velocity vector that is a result of those vectors. So again, this is kind of why we did that vector addition and subtraction in one dimension. Okay, so you're moving to the right at positive 7 meters per second, but somebody's pushing you left 1, 2, 3 times at negative 2 meters per second for every 1 second. So that would be 3 of those. So that would be total of negative 6. So your final velocity is positive 1. In a velocity versus time graph, you would start out at positive 7 meters per second, and you would end at positive 1 meters per second over that period of time of 3 seconds. So again, your initial velocity is positive 7 meters per second. Your acceleration, the slope of this line, is negative 2 meters per second for every second. And t is that. So if we take 3, multiply it by negative 2, we get negative 6, plus 1, plus 7 is equal to positive 1. Okay? So this is how vector addition and vector subtraction can actually help you create equations and find answers without using any equations at all, right? But I want you to do all three. I want you to be able to use a motion diagram and use a motion diagram to figure out a velocity versus time graph, and then do a linear fit on that to create an equation. Okay? Now, we're going to go to our little whiteboard here. I'm going to zoom in. So let's try this right now. Let's try to use equations to create, so these two equations to create a velocity versus time graph. And from that velocity versus time graph, we could figure out the displacement, and we could create a motion diagram. Okay? So let's try it. So here's what the problem is. It looks like you start out moving at negative 2 meters per second. Okay, so that's your initial velocity. Now your acceleration is positive, so they're going to be subtractive. So here we go. I'm going to count on this because it's not listed. It looks like it's by 1, so it looks like we start out here at negative 2 meters per second, and I'm going to use blue. Negative 2 meters per second on this velocity versus time graph. Now, over the period of 4 seconds, we're going to add to this. So we're going to add 2 to this. So 1, 2, and over 1. So this is your next second. 1, 2, and over 1. Next second, 1, 2, and over 1. Next second, and then 1. I think we need a extra number here. We need a positive 6. So, and then up 2 and over 1. So it looks like our final velocity is going to be positive 6 meters per second. And this is what our line is going to look like for the velocity. Oops, that looks terrible. Let's try this again. So we started out here at negative 2 meters per second. We went And acceleration is adding 2 velocities for every second, adding 2 velocities for every second. So after the first second, we came to a stop. And then what happened? Sorry, I'm going to redo a couple things here. I'm going to make these letters black. So this is positive 6 meters. Oops. Let's make that positive 6. And that is your final velocity at the 4-second mark. Okay, so you start out negative 2 meters per second. After the first second, you're not moving. After the second second, you're moving at positive 2 meters per second. And after the third second, it looks like you're moving at positive 4 meters per second. And then after the 6th second, it looks like you're moving, after the 4th second, you're moving at positive 6 meters per second. So let's figure, so we've learned curve fits. So we kind of pointed out what a curve fit is on a position versus time graph, which we'll get into in the next part. But I do want you to get used to constructing those. So again, we're making a line in a velocity versus time graph. So we're doing a linear fit, and that's telling us our acceleration and our velocity vectors. Now in a position versus time graph, we're now going to have bended parabolic lines. Okay, so they're going to be rounded. But if you know the acceleration here, that is the acceleration in a position versus time graph. And if you know the initial velocity there, that is the initial velocity in this equation. So in a position versus time graph, this is the equation we're going to be working with. In a velocity versus time graph, this is going to be a linear fit. We're not going to be working with rounded parabolics in a velocity versus time graph. So let's go ahead and figure out the displacement of this, okay? So we know in this first part, here is the displacement underneath the line, and we've done this before, okay? So if you imagine, and I'm going to zoom in on this, that this little triangle, which represents, so it's a triangle, and that's 2 meters per second, okay, over the period of 1 second. So if you figure out this is a triangle, which is a half of a rectangle, this blue area right here is going to be the displacement, which is going to be a triangle, which is a half of a rectangle, so that's negative 2 times 1 divided by 2. So this is going to be negative 2 meters per second times 1 second divided by 2. So that is going to give you, what is that, negative 2 times positive 1, so divided by 2, so that's going to be negative 1 meter displacement. This other area, relative to the 0 mark, is the displacement above the line. Okay? Which, again, this is going to be a triangle, so it's 3 over and 6 high. So 6 times 3 divided by 4, or in other words, positive 6 meters per second times a total of 3 seconds, which is going to be 2, 3, okay, so this is going to be 1, 2, 3, 4, so only 3 seconds, divided by 2. So this is going to be positive 3 times 3, so that's going to be a positive 9 displacement. So the total displacement, and we're going to use green to be consistent, is going to be equal to -1 meter plus 9 meters. So that overall displacement is going to be positive 8 meters. Now I don't know what the starting position of this is. All I know is it's got a total, it's got a displacement to the right of 8 meters over the entire trip. Okay? So that's how you could create two equations using one linear fit. We're going to use a linear fit on a velocity versus time graph to create this first equation, and this next one, which would be a curvilinear fit for position versus time graph, we're just going to fill in, since we know the acceleration, that goes here, since we know the initial velocity, that goes here. Okay? So I'll show you how to do that. We'll get more into curved lines when we get into position versus time graphs. Okay? Now, again, we had practiced finding addition of vectors, subtraction of vectors, and addition and subtraction of vectors with a modified scalar. Now, when we're going to go ahead and we're going to learn to add and subtract velocity vectors to find an acceleration vector, or add an acceleration vector to an initial velocity vector to create a final velocity vector. Okay, so I'm going to show you how to do that in this next exercise. Okay, and now these exercises, which we're going to do 3 of them together. Okay, but I'm going to, there's things that you're going to be asked for. Okay, you're going to be asked for the final velocity and displacement delta x. Okay, and we're going to create 2 kinematic equations, delta x and v final, using those. Okay, so here's what we're going to do. And this velocity is going to be counting by 1. So again, this is going to be -6 here, -6 meters per second there, and this is going to be +6 meters per second here, and this would be like +3 and -3, and this is over the period of 1, 2, 3 seconds, 4, 5 seconds. So this is the velocity versus time graph. We have 2 equations we're going to construct. Okay, and we have this situation. So we're given this initial velocity vector. We're given an acceleration vector. So this initial velocity vector is going to be, and I'm going to use blue for that. This initial velocity vector is going to be +6 meters per second. Let's use 1 block as 1 meter. So this is +6 meters per second. And let's call this, if it's 3 blocks, that acceleration, which I'm going to use red for that, is going to be a -3 meters per second over the period of 1 second. So that's -3 meters per second squared. Okay? And they're telling you this. This is going to happen over a period of 3 seconds. Okay? So let's create and let's do a couple things. Let's take our velocity vector. So we have an initial velocity vector, 1, 2, 3, 4, 5, 6. Okay, that's -6 meters per second. Now, we're going to subtract, oops, I should have started somewhere over here, because I'm about to run out of room. So let's start over here. 1, 2, 3, 4, 5, 6. So this is -6 meters per second. And we have an acceleration vector that is -3 meters per second for the first second. And then we're going to have another 3 meters per second for the second second. And now we have a third acceleration vector. This should be seconds over the last one. So we started here, we walked to the right 6 steps, walked to the left 9 steps, so that means we ended here. So the final velocity is going to be, and that should be a positive 6, is going to be negative 3 meters per second. Okay, let's create an equation here. Here's what I'm saying. That acceleration is going to be negative 3 meters per second for every second times delta t. But we started out with a positive 6 meters per second. Okay. And we could go right to this position versus time graph curvilinear fit. The first component is acceleration times time squared, so it's going to be 1/2 negative 3 meters per second for every second times time squared. And the next class, I think we get into why that is time squared. And then go plus, I should use blue, plus 6 meters per second times delta t. Times delta t. So you're supposed to construct those two equations. And if you look at this, that equation we made, it does follow that same equation that we made using the velocity versus time equation. So I want to get you used to constructing a position versus time curve fit using a linear fit from a velocity versus time graph. So let's figure out what this is going to look like graphically. We did it using vector addition. Let's try doing it graphically. So we started out at positive 6 meters per second. Now, we're going to be, after the first second, we should have dropped 1, 2, 3. So after the first second, we're right here. 1, 2, 3. After the second, our velocity is 0, which happens to be right here. And after the third second, we're going to drop 1, 2, 3, and we're now here. So this is going to look like a straight line where our final velocity is negative 3 meters per second. Okay. We could calculate our displacement vector. So again, if we let's do this first. If we use, let's calculate our final velocity just to make sure it's working. Delta t, so our time here is going to be 3 seconds plus 6 meters per second. So that is going to work out to 3 times 3, which is negative 9 plus 6, so that is negative 3 meters per second. If we wanted to calculate our total displacement, well, we're just going to plug in a 3 seconds here and a 3 seconds here. So 3 seconds squared is 9. 9 times 3 is 27. So 9 times 3 is 27 divided by 2. That's 13.5. So this is 13.5. So we're going to add that to 3 times 6, which is going to be, well, actually, hold it. That should be negative 13 point. Okay, hold on a second. Because this is negative 3. So it's going to be 9 times 3, that is negative, is 27, divided by 2, negative 13.5. And you know what? I'm just going to write that down. Negative 13.5 meters. That's this first part. And this is going to be plus 6 times 3 is 18 meters. So, what is that? Plus 18, 4.5. That is the total displacement, and it'll be positive 4.5 from the beginning to end. Okay. So in other words, it looks like this guy was moving to the right, it came to a stop, and it began moving to the left. So at some point, it had to come to a stop in its position versus time graph. Okay, so from starting to ending, even though it was moving all over the place, it only ended up moving 4.5 meters to the right. Okay, let's try another one. This is what you do if you have an initial velocity and a final velocity. Okay, so it looks like we have an initial velocity vector right here of positive 2 meters per second. And it looks like we have a final velocity. You know what? I'm going to put this is going to be equal to positive 2 meters per second right here. And it looks like we have a final velocity that is going to be 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So the final velocity is going to be positive 8 meters per second. So if our final velocity is positive 8 meters per second, I'm going to try to write that here. One, two, 3, 4, 5, 6, 7, 8. Here we go, which is positive 8 meters per second. How do we get this guy to be this positive 2? What do we have to add? Come on, don't do that. What do we have to add to this positive 2? How many vectors do we have to add to this positive 2? And we're going to need 3 of them. So we're trying to figure out the acceleration from this. This is why I like these problems. You have to figure out the acceleration based on what your information you're given. And you have to also figure out displacement. And you could use whatever way you want. I like using vectors. So what do we have to add? What size vector do we have to add to get this positive 2 to be equal to 8? And we need to add 3 of them. Well, there is one, so we got 1, 2, 3, 4, 5, 6 vectors. If we take 6 divided by 3, then we get an acceleration vector that is going to be positive 2. So each one of these is positive 2 meters per second for every second, right? Positive. This looks terrible. I'm going to zoom in and try to make it look a little bit better. So we're going to have to add 3 of these acceleration vectors, which is positive 2 meters per second for every second, another positive 2 meters per second for this second, and another positive 2 meters per second over this next second. And so there's going to be 3 of those because there's 3 seconds. So our initial velocity vector, which is 2, we're going to add 3 acceleration vectors, and that is going to be 8. So what that means is our acceleration is actually positive 2 meters per second. So let's construct our equation. We have a positive 2 meters per second delta t over the period of a second for every second times delta t, and our initial velocity was positive 2. So let's go ahead and just make sure it works. If we have an acceleration which is positive 2 meters per second for every second times 3 seconds plus 2 meters per second. Okay, well, this seconds will cancel out with this. 3 times 2 is 6, plus 2 is 8. So our final velocity is going to be positive 8 meters per second. Now we could actually go ahead and fill out this position versus time fit, okay, which is going to start out with a half and that acceleration again is positive 2 meters per second for every second delta t squared plus 2 meters per second delta t. So let's figure out our total displacement over this entire trip. So if this is going to be 3 seconds that we're going to square, or actually, I'm so sorry. Yeah, that is right. So that's going to be 9. 9 times 2 divided by 2, so that's just 9. That first part is just positive 9 meters. That's how much acceleration is adding to the initial point of when you are already moving. So this is going to be 3 times 2, which is positive 6. So this object will be displaced to the right a total of positive 15 meters. So ultimately, like if you had to draw that vector, you'd have to draw this vector, displacement vector, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it would have ended there, and that would be a displacement of positive 15. You don't need to draw that so much. I know it says you're supposed to draw it, but you're just supposed to use this area to do your vector addition and subtraction, given whatever information. Here we go. So yeah. On your velocity versus time graph, this is 1, 2, 3, so this is going to be negative 6. This is going to be positive 6 up here, and I'm just going to put a positive 3 and a negative 3. 0, 0. This is 1, 2, 3 seconds. That's all we need. Okay. Now we started out with positive 2 meters per second. Whew. And we're going to need to go to positive 9. So that's way up. That would be way up through here, which I need to make sure I give you velocity versus time graphs that actually fit your situation. Okay, but it would be way up here, and the total area actually, let's backtrack. Let's number this correctly. Let's number this by, let's number it by 2's. We're going to be kind of off a little bit. So this is going to be negative. This is going to be -2. -4, -6, -8, and -10. This is going to be +2, +4, +6, +8, and +10. So you have to number it, and this is 3 seconds right here. So when it was first moving, it started out here moving at +2 meters per second, and then the end, okay, in the end, it was moving at +8 meters per second. There we go. So and if you do this area relative to this data point, this point right here, this whole area, it's kind of weird. So if you started out here, this part of the area is going to be right here. Okay, I know that sounds weird, but this is, that area is +2. I should use blue. I'll try to get this. That area right here is going to be +2 meters per second times 3 seconds. So that's the tail end of this position versus time fit, which is going to be +6. The area above it right here is the area that is where the acceleration has added on to that initial velocity. So this area right here is the +9, right? So 2 times 8, or whatever, what is that? 2, 4, 6, 8. So what is that? 2, 4, 6, 8. So that is 6, and 6 times 3, +18 divided by 2. So this is the 1/2 +2 meters per second times 3 squared, which is going to be 9 seconds squared. So in other words, that is going to be 18. So this part right here is kind of weird, but this is going to be 1/2 of 6 meters per second times 3 seconds. So that's also equal to +9. Right there, right? And I don't know why I put a 9 there. That should be 3. So sorry about that. This should be 3 seconds that we're squaring, right? So, so in this part of the graph right here, this part of the graph, that's 1/2 times 2, 3 squared. So that's +9. Or you could just take this area right here, which is 1/2 of 6 times 3, +9. So that's how you can double check your mathematics using the graph too. Okay, So that is the end of our video for 1.5 acceleration using vector addition and subtraction in 1D. Okay, I hope you have a good day.